Okay, in another lecture I talked about autosomal chromosomes, which can produce autosomal traits. Genes located on autosomes control autosomal traits and disorders. Your autosomal chromosomes are the chromosomes that do not determine your sex. So we're talking about every single chromosome except for your X and your Y chromosome. So you can see that picture of that karyotype there, 1 through 22. Those are your autosomal chromosomes, and then the X and the Y, which would be the sex chromosomes. And there are autosomal dominant disorders, and there are autosomal recessive disorders. Autosomal recessive traits. Heterozygotes are carriers with a normal phenotype. Heterozygotes are carriers with a normal phenotype. And again, a carrier is somebody who has a messed up gene, but it isn't expressed in them because it's recessive. So like big T, little t. That little t may be messed up, but they have that big T, they have that dominant gene, which is overpowering the messed up gene. So they're fine. They do not have a genetic disorder. Most affected children have normal parents. So you can see right there, big A little a crossed with big A little a. Those parents are normal. They would be considered carriers. They have the recessive gene that's messed up, but they don't express it. They don't show it because they have a dominant gene which is overpowering the recessive gene. 2 affected parents will always produce affected children. 2 unaffected parents will not produce affected children unless both parents are carriers. So if you look at the first cross, there's no way they could have a child with the recessive disorder, but in the second cross, they wouldn't have a child either, but they'd be passing, they could have children who are carriers also. Affected individuals with homozygous, unaffected mates will have unaffected children. So someone could have a recessive disorder, but then have children who are fine because their spouse is homozygous dominant. Both males and females are affected equally. And here would be a pedigree chart. Okay, so you can see there are normal parents, they are carriers, so they're halfway colored in. They can produce a child that has the recessive disease. They produce children, possibly produce children that are carriers, and they can produce children who totally they're not affected at all. They're not carriers, they can't even pass the gene on. Examples of some autosomal recessive disorders: congenital deafness, some types of diabetes, albinism, that's being like an albino, that's a recessive disorder. There's something known as PKU, it's the inability to break down the amino acid phenolphthalein. They cannot have this amino acid in their diet at all, or it leads to severe mental disabilities. And if you look on the nutritional part on foods, it will list if it has phenolphthalein. Phenolphthalein is a protein, so these people cannot eat a lot of meat. Cystic fibrosis affects mucus and sweat glands, thick mucus in lungs, and digestive tract that interferes with gas exchange. It is lethal. 1 in 25 Caucasians are considered to be carriers of cystic fibrosis. A lot of times these people will survive until their mid to late 20s. Tay-Sachs disease, very horrible disease. It affects the nervous system. It's due to the lack of an enzyme needed to break down lipids necessary for normal brain function. Early onset. This tends to run in the Jewish community because remember at one time if you had Jewish people, they would only marry other Jewish people. So a lot of times that disease would kind of get spread through the community. But now you don't see that as much as you used to. Jewish people will marry outside of their religion, just like at one time Catholics would only marry other Catholics. But with this Tay-Sachs disease, it results in blindness, seizures, paralysis. The child is usually passed away by the age of 4, and it is a very horrible, horrible death to watch your child go through. Autosomal dominant traits. Heterozygous this time. These people are affected, big, little. Affected children usually have affected parents. You had to get that dominant gene from somebody, and you only need one dominant gene to have a dominant disorder. 2 affected parents can produce an unaffected child. if you look at that cross, if you did the Punnett square, you could see they could have little children. And this time, being little is the good thing, because having a big letter is causing a disease. The big gene, the powerful gene, is messed up. It has a mutation. 2 unaffected parents will not produce affected children. Both males and females are affected equally. And if you did a pedigree, there's no such thing as carriers, because if you're big, you have it. If you're big, little, you have it. If you're little, you don't have it. So there's no such thing as a carrier, because a carrier is somebody who has the gene, the mutated gene, but does not have any disease. Okay, a pedigree chart, you can see. So again, I did 2 parents that were there's no such thing as carriers, that are big little crossed with big little. They both have this disease. You pass it on, and a lot of people in the family usually end up with the disease because it is due to a dominant gene. You only need one of them to show the signs of it. Some examples: dwarfism, polydactylism, that's having more than 5 fingers, Marfan syndrome, I forgot hypertension, Marfan syndrome. Marfan syndrome is a disease, it affects the heart, it affects the joints, it affects tendons and ligaments. When these people figure out that they have Marfan's, they cannot play any kind of contact sport. If they get hit in the chest, they will immediately, their aorta will burst and they'll bleed out. There's all kinds of other signs and symptoms for Marfan syndrome. There's no one single test to tell if somebody has Marfan's. You have to do a battery of tests to figure out if someone has Marfan's. At one time, there were some historians that thought that Abraham Lincoln had Marfan syndrome. There's Huntington's disease, which is a nervous system degeneration resulting in early death, early being middle-aged, 40s, 50s. But a lot of times, by the time these people figure out they have Huntington's disease, they've already had children. And if you have Huntington's, you could just have one messed up gene, and you give that one messed up gene to your kid, the kid's going to have it. Another thing with Huntington's, a lot of times family members will think these people have a drinking problem because they stutter, they can't walk straight, and there's other neurological issues going on, but it's the fact that it's this disease breaking down their nervous system. Neurofibromatosis, which is also known as NF, they have these benign tumors all over the place, which a lot of times can end up on the brain or the nerve leading to the eye, and they can go blind. And also, like for hearing, it can get on the nerves there and cause them to be deaf. Progeria, drastic premature aging. It's very rare. A lot of times the people that have this will die by the age of 13. Okay, X-linked recessive traits. X-linked recessive. This is specifically just the X chromosome. X-linked, and most of these are recessive diseases, so I'm just going to talk about X-linked recessive traits. More males than females will be affected because males only have one X chromosome. If you have a messed up gene, it's messed up. You don't have the other X to counteract the bad stuff. An affected son can have affected parents who have normal phenotypes, and if you look at this, look real close, the way you write the genotypes, it's different. You have to put the male stuff first, so XY crossed with XX, male with female. And then you put the genotype for the disease as a superscript sitting on the X chromosome, because it's only on X. Men and women are different with the number of X's they have. So you can see there, the dad does not have it, and the mom would be considered a carrier. For the daughter to have the trait, to have the disease, her father must have it, and her mother either has it or is a carrier. So you can see the genotype for the father and the 2 possible genotypes for the mother in order for a daughter to have it. The trait often skips a generation from grandfather to grandson. If a woman has the trait, all of her sons will have it no matter what. Because guys get their X from their mom. Pedigree show only female carriers. Males cannot be carriers. Males either have it or they don't. X-linked traits are produced by genes only on the X chromosome. There are dominant and recessive, but we're only going to talk about X-linked recessive disorders. X big A versus the X little a. What would be the genotype of a male and a female that have a X-linked recessive trait and do not express those traits? Okay, so expressing the trait, males are X little a Y, females are X little a X little a. If they do not have the trait or the disorder, males have to be X big A Y, females could be X big A, or X big A, X little a. The second one there for the female, they would be considered a carrier. They don't have the disease, but it can be passed on to their child. And like I've mentioned, most X-linked traits are recessive. Okay, and so here we have a male is normal. The female is a carrier. We then have a boy who is normal, a boy with the disease, a girl who is normal. The other girl's normal, but she's considered a carrier because she can pass that gene on to her children. Some examples of X-linked recessive disorders. The red-green colorblind, being colorblind, difficulty seeing red versus green, blue versus yellow. On my website, I have a card that you can look at to see if you can see the number or whatever, to see if you can see it, then you're fine. If you can't see it, then it's a sign that you have color blindness. Hemophilia, also called the bleeder's disease. Absent of one or more protein necessary for normal blood clotting. These people, their blood does not clot. Some forms of deafness are considered X-linked recessive. Night blindness and muscular dystrophy. Some forms of muscular dystrophy is due to the X chromosome, a mess up on the X chromosome.